Hello everyone and welcome to lesson 10 on the Save My STEM Physics channel. Today we will be going over the 4 fundamental forces, which is another section on the particle physics chapter of the AQA specification, and these are the smallest possible division of forces. So these 4 forces actually are responsible for everything that happens in our universe, but they are only employed for use in particle physics because other forces sort of can be used to describe things on a larger scale. But the 4 fundamental forces which are employed in particle physics and which make up all of the forces are as follows: the strong force, the weak force, or what I like to call the what the hell force, the electromagnetic force, and the gravitational force. One thing they teach you at GCSE is that gravity is not a force, weight is a force, and whilst yes, weight is a force in mechanics, in particle physics there is the gravitational force. You will also sometimes see the strong force and weak force referred to as the strong interaction and weak interaction, but they are still the same thing. So what actually are these forces? Well, so if we take a look at strong first, that is either repulsive, so I will just put R/A for repulsive or attractive, between quarks and nucleons. So nucleons are any constituent of a nucleus, so neutrons and protons typically in a regular atom, and that is the force that keeps protons and neutrons together in a nucleus. It also can apply some repulsion between neutrons and protons, but that happens in a specific case, which I will go over in just a second. And that is what the strong force is. It is repulsion or attraction between quarks and nucleons. So how do we determine? I'll go over like sort of the nuances of each as we go through them. So how do we determine whether it's repulsive or attractive? Well, we have a graph which you need to know what it looks like for your A-levels, which looks like this. And on the top half, it is a repulsive force, and on the bottom half, it is an attractive force. And then we have distance between the nucleons, or distance between quarks, in femtometers. Femto is times 10 to the minus 15 meters, I think. It might be minus 12. Let me search that. Yeah, it is times 10 to the minus 15 meters. And yeah, so we have x-axis as distance, and then the y-axis as the force. If it's positive, then it's repulsive. If it's negative, then it is attractive. And the graph looks a little bit like that. So you'll see it crosses between repulsive and attractive here. So you need to know at what distance that happens. You also need to know at what distance there is a turning point, and you need to know at what distance it hits 0. So it has a range. It only works, it only actually does things in a certain radius around whatever's causing it. So first of all, it crosses the x-axis at 0.5 femtometers. It turns around at 1 femtometer, and it stops working at roughly 3 femtometers. And that is the ranges on the strong force. So if it ever asks, if you ever get an exam question asking you about um, repulsion or attraction due to any of the fundamental forces, and it asks you to name the fundamental forces, then you are expected to recognize that it can repulse things below 0.5 femtometers, and it will attract things between 0.5 and 3, and it will do nothing after 3 femtometers because it has a range. It is due to its, well, like on a naming basis, it is the strongest of the four fundamental forces, so that's relatively easy to remember. However, the weak force, which we were about to get onto, does not follow that. The weak force is not the weakest of the four forces. So, the weak force, now that we're onto it, is what I like to call the what the hell force, as I mentioned earlier, because physicists don't actually really know what it is. I'll just move the page up preemptively. They don't actually really know what it is. But what we do know is that it causes radioactive decay. So, stuff like alpha decay, beta plus decay, beta minus decay. Well, actually, is alpha decay? Alpha decay is. I take back what I said about alpha decay. I'm actually not certain about that one, but beta plus decay and beta minus decay, which is stuff that you should have met at GCSE, or at least just beta decay you should have met at GCSE, and also electron capture, which is something new, are governed by the weak force, and they are forms of radioactive decay. And uh, we will get on to radioactive decay and conservation laws and the weak interaction in another lesson. But for now, that's all I will go over, because if I go over that stuff now, this lesson will be way too long. And it's not the weakest of the forces. It does have a range, which I actually don't have quoted, I think. Oh no, it has a shorter range than the strong force at 10 to the minus 18 meters. So that's like right there, like right on the y-axis, basically. It's got an absolutely tiny range. And moving on to the electromagnetic force. Don't say electrostatic, you will not get the mark for that. So electromagnetic is repulsion or attraction between charged particles. So strong happens between quarks and nucleons. Weak happens in quarks and nucleons for beta minus and beta plus decay. It happens with leptons for electron capture. And electromagnetic is between any particles which have a charge. So notably not neutrinos. Neutrons don't have it, but the quarks inside them do have electromagnetic force. And yeah, so anything with charge experiences the electromagnetic force, and I will demonstrate the electromagnetic force on the same axis. It is going to intersect the 0.5, but oh well. And the electromagnetic force kind of looks like that line there. It never touches the x-axis because it has an infinite range. So a proton, like 10 billion light years away, has the tiniest attractive force applying on electrons on our Earth. But obviously that force is so tiny that it is negligible, but it does have a theoretically infinite range. And yeah, so it is stronger than the wait, is it? It's stronger than the strong force past 3 meters, because of, you know, yeah, sort of makes sense. And Yeah, so I think that's all we need to go over the electromagnetic force. Just don't call it electrostatic. It is electromagnetic because it causes electricity and magnetism. It doesn't just cause electricity. Um, and that is how its force works. It's repulsive. Obviously, if it's attractive, it will just be a mirror line of the same thing. Um, and obviously not touching the x-axis. So if I just draw that on for you now, that's what that should look like, and pretty self-explanatory. Um, yeah, so that's everything that we need to go over the electromagnetic force, and the final force that we have to go over is gravitational, not gravity, gravitational. I'm not sure if that can get you marked down, but better to be on the safe side, and that is between particles with mass. It is the weakest of the four fundamental forces. In fact, it is 10 to the 29 times weaker than the weak force, which is already incredibly weak. So, in the grand scheme of things, the gravitational force is absolutely tiny, but it comes on to form these incredibly uh, useful and sort of important forces, such as the gravity on our Earth. Uh, and that's basically all you need to know about the gravitational force, because again, uh, yeah, physicists don't really know. One time last year, a student in my class asked my physics teacher uh, what gravity is, and he replied, "Magic space gnomes keep everything in place." So that hopefully should give you an understanding about what we actually know about gravity, aka not much. We will get onto exchange particles for each of these forces next lesson, but it's important that you know about each of the forces before you get onto the exchange particles, and after that we'll get onto annihilation, pair production, and Feynman diagrams, which are very exciting. Hopefully this lesson has made things clear enough for you about the fundamental forces. Those are the four that you can be asked to list them off, and this is the graph that you need to know. You need to know the distances, but you don't need to know their relative strengths to one another. As a numerical value, you just need to know which ones are strongest and which ones are weakest, and what they do. So, hopefully this has helped. Thank you very much for watching. I will see you in the next one where we are talking about exchange particles. Bye bye.